Hello, I'm Jose Franco and I am an integration engineer at Offchain Labs. In this video, I'm going to show you how you can get started with Stylus by writing and deploying a smart contract written in AssemblyScript. We will go through all steps involved in the process, from configuring your development environment to writing and deploying the contract, as well as knowing the tools that you have available to work with Stylus. So let's start by explaining what is a Stylus. Stylus is a new technology that lets developers write smart contracts in Rust, AssemblyScript, and other programming languages, making it more efficient and cheaper while maintaining interoperability with the EVM. That means that with Stylus, you can write your smart contracts in, for example, AssemblyScript, and still interact with all of the contracts written in Solidity or other languages. The way this works is through a format called WebAssembly, which was originally designed for the web, but that we leverage in Stylus. Supporting WebAssembly means supporting any language that can compile to WASM, and there are many that do so. At Offchain Labs, we are working to simplify the process of writing smart contracts in those supported languages, and we do that through SDKs. At the moment, we're focusing especially on Rust, but I'm going to show you how any language can also use this technology. So let's get started. The first tool that we're going to install is the Stylus Cargo Crate that provides several tools to check and deploy our Stylus contracts. We'll need Rust to do so, so we'll start by installing Rust. Now in this page, we can find an installation guide for Rust. When you visit it, you'll get the installation instructions corresponding to the operating system that you're using. For me, I'm using Windows, so I get Windows instructions. And I'm actually using the Windows subsystem for Linux. So I'm going to use this command here. I'm going to copy it and run it in my terminal. And there we go. Now we are going to add support for the WebAssembly compilation target in Rust by running the following command. So Rust app target add 1032 unknown. There we go. And now that we have Rust installed, we have access to Cargo, a command line tool that also acts as a package manager for Rust. With it, we can install the Stylus crate. So we go cargo install, cargo Stylus. There we go. I already have it installed, but anyway, the process is straightforward and you don't need to do anything else to install it. Okay. And there we go. So if everything is correct, we should now have access to the Stylus CLI command. There we go. All right. So let's move now to AssemblyScript. Now, AssemblyScript is a TypeScript-like language designed to be compiled to WebAssembly. It is TypeScript-like because the syntax is basically the same as TypeScript. The difference is that because their targets are not the same, JavaScript for TypeScript and WebAssembly for AssemblyScript, the available standard libraries and APIs are also different. They handle different runtime environments, and even the typing mechanism is more strict in AssemblyScript. However, they are similar enough that any TypeScript developer will find it very easy to understand and work with AssemblyScript. So let's now go and create our AssemblyScript project. So we're going to create a folder first. There we go, and let's cd into it. Now the only requirement for this example is to have Node.js installed, because we will use the package manager npm to install AssemblyScript. If you don't have Node installed, you can go to nodejs.org and follow the instructions there to install it. So let's start this project with npm. There we go, and let's now install AssemblyScript. And now we create an AssemblyScript project, which is the default options, and that's it. Okay, so now AssemblyScript has created a set of folders and a minimal example for us to work with. Let me explain a bit what these folders and files are. There we go. So first we have the assembly folder, which contains the AssemblyScript code of our program. Then we have the build folder that will contain all the compiled WASM files, the tests folders that will contain the test files that we want to use for our project, and the configuration file. This configuration file has all the configuration options that we use when compiling AssemblyScript to WebAssembly. And we are going to change a few of these options so our smart contract can work with Stylus. We're going to use these options right here. There we go. So first, we're going to disable the bulk memory WASM feature, because when compiling with this option, it uses the data count section of WASM, which is not supported by Stylus yet. Second, the runtime variant to use must be either minimal or stub. Otherwise, if we use the default, Stylus won't be able to handle memory instructions effectively. And finally, we need to declare a custom abort function, because the default one from AssemblyScript does not behave correctly with Stylus. Okay, so now that we have the options set, we can go and work on our first AssemblyScript project. So let's start with a very basic example that is going to just return whatever call data we have received in the smart contract. To do this, we need to have a way to obtain the call data and also write some values in return. To perform these kind of actions, Stylus provides a series of hooks, or also known as host IOs functions, that help us access functionality of the host EVM environment. So we are going to use these two hooks, these two external functions. Let me remove all these first. There we go. And these functions are read args and write result. We declared them like this with the external decorator, so WASM knows that they will be available when running the smart contract. Now also Stylus expects a specific function to be the entry point for the smart contract. So we're going to declare it here. Let's write a small comment here, Stylus entry point, and declare and export a function called user entry point. Now, this is a special function. It needs to be called like that, user entry point, and receives an integer parameter, and actually an i32 parameter, which will be the length of the call data received, and it returns another i32, which can be either 0 if everything worked correctly, or 1 if there were any errors. Okay, so for now we're just going to return 0. Alright, so now, how do we actually get the call data received, and also how do we write it out? To read the call data, we're going to use the external function readargs. This function expects to receive as a parameter a pointer in memory where we want to write the data to, the call data that we received. Because in all EVM calls we always receive a set of bytes, we're going to use a data structure that makes it more convenient to handle bytes. We're going to use an array of 8-bit unsigned integers, which in JavaScript and AssemblyScript is called a uint8 array. So we're going to create a new array, call it input, with length equals to the length of the call data we are going to receive. Now in AssemblyScript, this type uint8 array includes one very useful property, which is the point in memory where the data handled by the array starts. And this is exactly what we need for the readargs method. So we're going to call the readargs method. We're going to pass the input, and we're going to use the property data start to transform it into an unsigned 32. Okay. Alright, so with this, we now have the call data received in the smart contract in this input array. We can do whatever we want with it. But let's keep it simple and just return those bytes as a result of the smart contract's execution. So we're going to use the write result function for that. And this function expects two parameters: a pointer in memory where the information to be written as output lives, and the length in bytes of that output. Okay, so we are going to just return the input array, also as u32, and the length in bytes of that array. There we go. Okay, finally, there is one last thing that we are missing for, which is the custom abort function. We said in the config file that we were going to use a custom abort function, so we need to declare it here. And we're going to use this default function. It's just an empty function because we are not going to use it for now. So with this, we make sure that Stylus will be able to call the abort function if anything comes up. Okay, so now we have our basic smart contract written, and let's compile it with AssemblyScript. So we're going to bring up the terminal again, and we're going to use npm run as build there. Okay, and now let's use the Stylus CLI tool. So let me explain a bit what this tool does. We can use this tool to perform several actions for our Stylus program. Two very useful commands are the check command, which analyzes the WASM file and verifies that it can be deployed and work with Stylus, and also the deploy command, which will actually deploy the smart contract. So let's first use the check tool. So to use the check tool, we just call cargo stylus check, and we pass the argument WASM file path with the WASM file. Using the build folder because it's where AssemblyScript generates the compiled file, and we're using the release.wasm because it's the file, the default file name of AssemblyScript. And it looks like we have an error. We are missing an import. We are missing the import memory growth. Okay, for Stylus to effectively manage the memory of the smart contract, it needs to have access to that function in the generated WASM file. So let's add it as an external function in our code. Okay, let's add it down here below. There we go. But if we leave it like this, it won't be compiling to the WASM file because it's not being used by any exported function. So let's create a dummy one. Let's create, for example, an exporter function mark used, and just call memory grow 0, and that's it. Okay, let's now try to compile and check again. So we run again the compiler. Perfect. And now we check our file. Okay, and it works. If the check doesn't return any errors, it means that the compiled WASM is compatible with Stylus. It says here that the code is already activated on chain because I did the same test before. If your code is new, it will just say that the code is valid. Okay. All right, so let's finally deploy it to the blockchain. To do that, we need a private key, right? So I'm going to copy one that I have from another example, and here, there we go. So you just copy the private key into a file. You call it whatever you want, and we are going to use it in the next command, right? So we're going to do stylus deploy. We're going to use the same argument as before, and we're private key down here. Private key. There we go. Okay. Now it is deploying. Because my program is already activated, it's not doing the activation step. But if your code is new, it will just have two sections, one for deployment and another one for activation. So there we go. Our smart contract now is deployed into the blockchain. So let's go and test it now. Okay, to test it, we can use whatever tool we want. We can use Ethers.js, we can use Foundry, whatever we normally use to interact with the blockchain. In this case, because it is a very simple smart contract, we are going to use the cast command from Foundry. Okay, so we're going to call cast call RPC URL. We're going to pass, the RPC URL of Stylus testnet. And we're going to use our address, which is here. And we're going to pass a set of bytes here. There we go. So we send this set of bytes, 0x12345 and we got the same in return. If we use other bytes, there we go, we get the same. So it works. Our very basic smart contract works. All right. So let's now do something a bit more interesting. We're going to change our smart contract and we're going to implement an algorithm that finds prime numbers using the sieve of Eratosthenes. Specifically, we want to find the highest prime number up to a number that we will receive as call data. Now, I'm not going to explain how the algorithm works, but we'll see how to take our input bytes, pass them through a function, and return the resulting number as bytes. Okay. To do that, we are going to create a new file here called functions, because we are going to put all these functions in here. And I'm going to paste all these functions that I have here. I'm going to explain that now. All right. So there are 3 exported functions here, but the most important one is this one, get max prime up to. This is actually the function that implements the algorithm. Okay. So this function actually doesn't work with bytes, but only with numbers, as we see here. And it receives one integer and it returns another integer. So we need to find a way to convert the bytes that we receive to numbers that this function can handle. And also the inverse process, because we need to output bytes, not numbers. To do that, we can use these 2 functions that we have up here. One is bytes to i32 and another one is i32 to bytes. So bytes to i32 takes a set of bytes in a uint 8 array and returns the number representation of those bytes. And i32 bytes does the inverse process. It takes a number and returns the bytes representation of that number. Okay. So now we are going to change the index file to actually use these functions. After reading the call data that we receive, we're going to convert that call data into a number. And we'll do that by calling bytes to i32 with the input array. Once we have the number, we will call the search function for the prime numbers, right? Get max prime up to input number. There we go. And we finally will convert that number into a set of bytes that we can output with i32 bytes output number. There we go. And finally, we will just write the output out. Okay, let's now compile it and see if it works. Let's call npm run build. There we go. And let's now check if everything is correct. Okay, and let's actually now deploy it. We will use the same command as before because we compiled to the same file. All right, perfect. Now, to test this new contract, let's do something a bit more user-friendly, because we don't want to be sending bytes to check to find prime numbers, right? So we're going to create a very basic JavaScript file that calls the smart contract through the ethers.js library. Because we're going to use ethers.js, we need to install it, right? npm install ethers. There we go. And now we are going to change this file. We're going to remove all these, and we're going to use this. It is a very simple code. We receive a number as a parameter here. We pass it as to the main function. The main function instantiates a new RPC provider through ethers.js, and we call our smart contract here. We transform that number into the hexadecimal representation, the bytes actually, and we do the inverse process with the result. We parse those bytes into an integer, and we just console log that result. So the only thing that we need to do is actually specify our smart contract address that we have in the terminal here. There we go. Okay, let's now check our contract with the test file. So we're going to do node test index.js and just one number, this one for example. All right, so we passed 56 and we get 53 in return, which is correct. And then we can use another number, for example, yeah, this one. We get another one. All right, so we can use the actual prime number, so we get the same result. And if we get the one below, there we go. These are actual prime numbers. We can check in Google or any other way you want. All right, so there we go. There we have our first smart contract with a complex algorithm implemented on-chain with Stylus and written in AssemblyScript. This code is also available at this repository that I'm going to show you now. Here. This code has a few changes, so it is a bit more dev-friendly, but it has the same example there. And also, if you want to learn more about Arbitrum Stylus, you can check the documentation here. There's a nice introduction to it. There is a quick start in Rust. And there's also our Discord and Telegram channels for developers. So I invite you to check them out and try this example and start writing your code with in Arbitrum Stylus. So that's it. I hope you enjoyed this presentation and see you next time. Bye.